So our venue and food sponsor is just one group, Integra Chain. Right? So does someone want to give a quick shout out for what you do and how you do it?
Yeah, I can do it. So at Integra Chain, we are a data company. We deal with several hundred data streams we have coming in. We got interested in Scala a few years ago. We built a order management system that's processed $50 billion of orders in Scala. They all flow through our system and flow back out. Our current data pipeline has been written in Perl and SQL and old school stuff, and it's a lot of work to rebuild our data pipeline, but we're starting to write new bits of processing in Scala, and Marcus has come on board and is doing that. And we're happy to have you all here and happy to support the Scala community. And if you're interested in working with us, we're also looking for people, so feel free to stay in touch.
So I think that's it. I don't think there's any other. So one other announcement is at the next meeting, if there are enough entrants, we're going to have a Scalatron battle. So people that were at the last meeting and saw what that is. If you don't know, just again reach out on Meetup or shoot a message to the mailing list, and we can bring you up to speed. It'll be a winner-take-all contest with potentially fantastic prizes. But probably not. Probably entirely pedestrian prizes. All right, so Marcus Henry is our speaker tonight, and he will be talking about actors and
futures
and futures and composability of monads, I imagine, somewhere in there.
Yeah, without using the words, Sure. That's how I do with all my talks. Yeah.
All right.
Yeah, don't use the mathy words.
Yeah. So again, thank you all for coming. I got to step out about halfway through, so
yep.
I'll say my goodbye now as well.
Later. All right, so asynchronous computing, So computing started synchronously, right? You do one thing, you do another thing, you do another thing. It all happens in a line, and then you get a result. That's it. So that's what we're going to start with. We're just going to start with computation in general. And then we're going to slowly build up to higher and higher forms of abstraction until we get to actors, which are a pretty high form of abstraction for asynchronous development. All right. So yeah, computation. Computation takes arguments, and then it returns a value. But this isn't the only thing that's important for a computation. The third part of this is the duration of the computation. And the duration matters because if you have constraints on, you need to get a certain amount of computation done in a certain amount of time, and then you have 3 of those computations to get done, now you have a problem, right? So functions help us to abstract over a computation, right? We pass in different arguments, get out different values. You don't have to run a static program. You can pass in different things, and we do that with functions. So how do we abstract over duration, right? That's kind of what we're talking about here. That's complicated, and that's really, really complex, and we don't really care about it because Scala does it for us. All right, so futures. They provide meaningful abstractions for handling duration, right? So you have your computation, you have how long your computation takes. These are different things. They used to be one and the same. We used to take for granted that we knew how an application would execute at runtime. You could prove a program. Anyone who's old enough probably remembers doing that, proving a program on paper in C before you actually get to a computer and write it. I've done it before. It really sucks. It's terrible. No one does that anymore because you can't really. Things have gotten too complicated. So it helps you to perform multiple operations at the same time to solve, your queuing issues and things like that. So these are the types of things, the types of problems that we can solve using futures. And we're just going to use some pretty basic mathematic operations just to show how this can work. All right, so take factorial. Everyone knows factorial. You just multiply all the ants that are less than me down to 2, and then I get a result. So this is the normal version of factorial. Nothing too surprising here. And we turn a big int because int is not big enough for us. This takes a really, really, really long time to execute anything. I only went down to 10,000 factorial because already we're at, 100,000 factorial linearly on my machine. I cut it off at a half hour. It took, like, the time here blows up. It scales like shit, basically. You can't do anything with this. There's no reason for you to do this. So futures give us an out for this. All right. So let's make it asynchronous. The first thing people do normally is they take the entire operation and they just wrap it in a future. And they say, okay, I'm writing asynchronous code now. I'm done. So what this gets you is you can, it's kind of asynchronous. You can do other things while this long computation is happening, right? So it solves one very basic problem. If you have to do 3 of these at a time and you have 3 cores, it's going to take the same amount of time as if you only have 1 of them to do. So that's the only problem it really solves. It doesn't really solve latency issues with if your user needs that result in 10 seconds, you got a problem, right? So that is the new free lunch, this. It kind of gets you halfway there, Developers sometimes use it and think that they're doing a good thing, but they're really not, Yeah. And this little thing, execution context, all futures need it. It's just something that Scala needs. It's basically just says, here's a thread pool, run your futures in this. That's all it is. You don't have to really worry about it. This is one of the things that, like in a couple slides ago, I said, Scala does this for us. So this is one abstraction layer that we don't need to worry about here, is how do you deal with multiple threads, how do you schedule them, how do you queue them, all that stuff. Don't need to worry about it. All right. This still takes a really long time, right? But at least it's in the background, like I said before, So we can do better here. We can do much, much better. We have to realize multiplication is associative, right? So that gives us a way where we can split this up a little bit, right? So here we've got let me try to do this. So here we take a part of it, right? So we take a low value and a high value. And what we do is multiply from that low value to that high value, right? So our recursion here is partial, So we're taking it in chunks. We're just chunks. And then here we're doing, we're taking the partials and then we're folding over them, right? From 1 all the way up, we get our values, right? All right. And this function here, just take my word for it. It just takes 10,000 at a time, right? So we're doing this in chunks of 10,000. 10,000, we take 10,000 ints, we multiply them all together, then we take the next 10,000 ints, we multiply them all together, and then we take those two, we multiply them, and then we have a result, right? So this gets us, a kind of a sort of breakup among our parts here, right? So using this process, even without putting it in a future, does better. Breaking up the computation into those parts helps us here. So this is a little bit more computer sciencey than we need to get into here, but because the numbers are so large, there are more than one multiplication operation happening for each multiplication operation, because the computer has to break it up into the distinct words. So that's why we get a little bit of speed up here. We're not quite there yet. We're not doing asynchronous, but it does a little better. So when you see something like that, don't be alarmed. It's just an artifact of computation. It still won't scale because we're still synchronous. All right. So to make it asynchronous, we start with our synchronous code, right? So we take our 10,000 at a time, we do our identity, and then for each little piece, we multiply it with the previous piece, little bits at a time, right? How do we convert this directly into something with futures, right? We have two issues really, right? We need an identity, and we need a way to combine values, right? With multiplication, the identity is easy. It's something that we take for granted. We know this from grade school. You multiply 1 by any number, you get that same number back. So we know how to do this, and we know how to multiply things together when they're ints, because we also know that from grade school. But when you try to do this asynchronously, you bring the computation into the futures, where do we go, right? Scala provides some operations for us to use, right? Future.successful just returns whatever you pass into it as a future inside of an already completed successful future, right? So since 1 is our identity for big int, future.successful1 gives us an identity for future of big int. And future has map and flat map. So we can use for comprehensions to combine futures together. And then inside of those futures, once we're inside of the for comprehension, we can just use our regular multiplication operation. So this breaks out really nicely for us. It's pretty straightforward. All right. Now we actually are asynchronous, right? We have all of these different pieces that we do, and we're wrapping them each in a future, each little piece we put inside of a future. And then we multiply the parts together from the previous multiplication, this current one, we multiply it together, right? So now we're asynchronous, right? Not quite. This has the same exact runtime characteristics as the last attempt, even though we're wrapping everything in futures. Does anyone know enough to look at this and tell me what's wrong with it? Okay, good.
B has to wait for A.
Yep. This is sequential. When you put things inside of a for comprehension, so for comprehensions, all they do is they compile the first pass of the compiler, turns them into a series of flat map calls and map calls. That's all they do. So this second future is happening inside of the flat map for the first future, which means it waits for the first future to complete before it starts to execute, right? So what we need is to take this future inside and move it outside, right? So when this is well done, we see here that we just put this future into a variable, and then we do our for comprehension here, and we multiply like before. So recall when we were synchronous, we had this runtime characteristic, right? For 1 million factorial, it took about 2 minutes, just under. Now, we'd expect that, I have 4 cores, so we'd expect that to be around 30 seconds, right? We get 5 seconds back. What did I do wrong? What's wrong with this code? Yeah.
So I was going to ask an unrelated question.
Yeah.
Like, would you, I mean, could you just map over the buckets and map them to futures and then fold over the futures?
Yep. That's what we did wrong. This is still sequential. The multiplication between all the different buckets is still sequential. So even though you're doing, each individual part in parallel, when you bring them together, the in-between parts are sequential now. So that is where the bulk of the time comes from. Because remember when we took the synchronous computation and we broke it up into the buckets and it was faster, even though we hadn't made it asynchronous, is because the larger the numbers are, the longer they take to multiply together. So this is taking the largest of all of the numbers and making that part synchronous. The smaller portions are asynchronous. So that's why we don't get that big of a performance boost from doing this asynchronous. So once more, algebra saves us. Multiplication is commutative. So we can rearrange these in any order we want, multiply them together, and we still get the same result. So why don't we take it half and half? Do a left side and a right side, put them together. And then recurse into that, take the left side and the right side, put them together. All right. So this is in a few parts. So the way we do this is we map, like Martin said, we map over to get a sequence of futures, right? And then we got to break those up. How do we break those up, right? So we accumulate them, and then here we go. We got to determine what we have first. So if we have more than one, then we want to break them up into a left side and a right side. That's what this collapse function does, which we'll go over next, right? If there's only one of them, we just return it. Otherwise, we return the identity, which is future successful of the big N identity, right? And to split the pot, this is all we do. So I'm just taking them 2 by 2. I'm going to like the lowest possible level. Every 2, we're going to do that in one future, and then that's going to bubble up to another future, and that's going to bubble up to another, and that's going to bubble up to another, until we get our entire computation. So we're basically just building a binary tree of multiplication objects here. Yeah. All right, so what do we expect our runtime to be now? Right? We'd expect it to be, since I have 4 cores, we expect it to be 30 seconds, right? 10 seconds. So again, going back to that one weird slide, the bigger the numbers that you're multiplying, the longer this takes. So we're multiplying 2 by 2 now, So we so instead of taking the first one, the first chunk of 10,000, multiplying by the second chunk of 10,000, that creates a giant number. Multiplying that giant number by the third chunk of 10,000 creates another even gianter number. Multiplying that by the next one, we're taking 2 chunks of 10,000, right? Multiplying those. The next 2, multiplying those. These are still relatively small. And then we're taking smaller and smaller numbers and multiplying them 2 by 2. So that's where this extra speed boost comes from, right? Yeah, go ahead, Martin.
I'm just wondering,
Or, yeah.
is there an underlying algebra? Is there a group
that you're defining the operation over? Like,
Well, yes. So yeah. I mean, the group is just the real numbers under multiplication.
yeah.
Yeah.
But for a specific n, there will be
Yeah.
group for that. So you're defining.
Yeah. That's pretty much what.
Yeah, okay.
Yeah.
Okay,
Yeah.
good.
But like I said at the beginning, you know, I do these talks without using the math words.
Okay,
Yeah.
yeah.
But that's exactly what we did. We
Good.
defined an identity. We designed a way to combine them. That's
Okay.
So yep. Yeah. Go ahead.
So you skipped over get buckets, right?
Yeah. It just breaks them up by 10,000. Just
And then you're doing like basically sequential buckets.
Yeah.
You keep mentioning how as the size of the big ends
Yeah.
grows, it gets slower and slower. So
Yep.
can you, for instance, interleave the buckets?
Yeah, that would give you a lot more performance.
Only
too.
in the domain
Yeah.
of factorial, for instance, or something
Yeah.
like that.
Yep, that would give you a lot more speed here as well, but I just want to keep it simple.
I was just curious.
Yep. Okay, so far we have a linear computation. We broke it up in smaller computations, wrapped them into futures, and then broke them up into a hierarchy, right? This was our process for taking something that was sequential, something that's naturally sequential, and trying to get some more performance out of it by making it asynchronous, right? Small computations in a hierarchy. That made it pretty simple for us, right? Straightforward. All right. That was a lot of work. You know, is there a better abstraction for this type of computation, right? So that leads us to, let's try our hand at actors. Maybe actors can help, you know. This is another abstraction for asynchronous computing, right? It's meant to solve the problem of taking a hierarchy of very small computations and aggregating them up. That's the purpose of actors, right? So there are a couple problems, you know, just that it's not typed. The actors aren't typed, so you can't use the compiler to help you, you know, figure out if your program is correct. But I mean, there are ways around that with testing and just discipline around how you build your actors and all that stuff. So we're not really worried about that. We're assuming that you're able to get used to things, that you adapt. You know. All right. So the question here is factorial a good candidate for actors? It has both of the things we look for. You know, small computations in a hierarchy. And that's what we look for to make something, to shove something into an actor system, right? It's not. The reason is we kind of shoehorned it into this form, you know. The factorial computation is naturally just this linear thing that happens, you know. It's a multiplication after a multiplication after a multiplication. It doesn't present itself in this form. So this is one of the hardest things about asynchronous computation, is there are so many ways to do it. You know, which problems can I use for which solutions? Like just gaining that insight takes a long time. It's not something that you're going to really learn from a book. You're going to learn this from using the wrong abstraction 100 times and figuring out, oh, that's why it's wrong, you know, for my situation. Or building an entire application built-in actors, and then watching it just blow up horizontally, and then realizing that you should have just written a bunch of futures. You know, that's where it's going to, like, you have to go through the pain. But there is like an intuition that you can gain here, you know. Just if you have an abstraction, right, and you have to force your problem into it, it's a bad abstraction. That's all. You know, that's the first step. So if you just keep that in the back of your mind, you know, every time you look to build something in actors, or every time you look to build something in futures, just in the back of your mind, am I forcing this to happen? Or is it just falling out? You know, that's how these things are written. They're written to be very, very easy. They're written to be very, very smooth. They're written so that you as the developer can build an application with very little pain. So if there's a lot of pain, you should probably try to find a different abstraction. Yeah. All right. Okay. So our example can still be used here when we venture into actors. We just need to find something that has as its building blocks actors. Factorials, right? We're going to do n choose k. So n choose k is 3 factorials smashed together, right? It's hierarchical. It's got n factorial, k factorial, and n minus k factorial, which we know how to compute asynchronously. We just did that. And it's a 2-level hierarchy, right? You do the numerator and denominator at 1 level of the hierarchy, and then the denominator is itself another hierarchy of 2 computations. So this pretty naturally fits into our actor system model. All right. So some design up front. Go ahead. Yeah. Question.
Go back a slide.
Yeah.
My brain might have broken, but should the result be A divided by B?
Yep. It should be. Yep. My bad. Yep. All right. Moving on. Yeah. A times D should be A divided by D. Yeah. Okay. So some design up front. All right.
Can you explain one more time why the factorial is not a good fit?
So, factorial is not a good fit because of this slide. To get it into a form where it makes sense to split it up into actors took a lot of work. You know, it's not like if you started out with the original sequential program, right? It's to get to an actor system that will outperform that sequential program. It took so many steps, you know. It took a lot of code. It was like we had to force it in there, you know. You can divide it into actors because it is a hierarchy and stuff. I'm just saying it's not your first. It shouldn't really be your first choice.
So when you say that it has to be hierarchical and simple computation, are there other conditions? Because it's hierarchical and simple computation, but is there some other condition on it that makes it not a good solution? If you're going to be
yeah, there are. So in my day-to-day, really, when I build an actor, one of the questions I ask myself is, does it make sense to offload this computation, this other part of the computation that I'm going to spawn an actor for, onto another system instead of right here, right? So that means, does it make sense for me to incur the network traffic of sending out that I need a computation done and receiving the result of that computation back? And recall, so we're doing factorials, right? We're doing millions and millions. These numbers are gigantic, right? These numbers are in the megabytes if you make it a string, right? So it may not be worth it to ship that over the network. So there are other things here because actor systems work really, really well for distributed computing. Futures do not. So if you have to be distributed, futures are a bad abstraction because you'd have to write a lot of code to force futures to work in that situation. Because you could do it, it's just it would take you a lot of code, right? So like here with factorial, it took a lot of code to get it into a form that would be okay for an actor system to outperform the sequential code. Yeah. All right. Yep. All right. So.
So
Yeah.
the key issue is that the intermediate results are so large that they're large messages, so they don't make sense for actors as much.
Yeah. Mm-hmm. Yep. They don't make as much sense. All right. So a little bit of design.
Just to say it one more time.
Yeah.
It was a hierarchy and small computations at the first step. But as you start to combine them up,
Yeah,
it's
it
no longer
gets.
true.
Yeah. Mm-hmm.
Okay. Thanks.
Yep. That's another way of looking at it. It's like it's not always small.
Yeah.
It's most of the time small. It's just a weird thing to force into that situation. Yep. Yep. All right. So like we said, we've got this hierarchy. There's a numerator and denominator at the first level of it. And then the denominator breaks up into two other operations for this right here. All right. So actor systems work on message passing. So we have to build messages. So we're going to build those messages, and we're going to name them accordingly. We have our numerator, our denominator, our left side of the denominator, and the right side of the denominator. And they are n factorial, k factorial times n minus k factorial. Also, so a little side note, in Scala, you can name things whatever you want if you put it inside of backticks. So this does compile, actually. Yeah. I like to just name things what they are when I'm doing math, just so I don't get confused. Like, because if you name things A, B, C, D, it's overwhelming. It can get, yeah. So we have a helper method just to do our factorials and what we're going to do on success and failure. You know, so futures can also be composed in this way, where you do something and then you can say if it succeeds, you do something else, right? You perform some other computation. If it fails, you perform this other computation, right? So you can also combine futures that way. It's not just map and flat map. But this pretty much works like a pass-through. Yeah. All right. Okay. So the first actor is the entry actor, right? So to compute a combination, right, we need a few things. First thing we need is an execution context, because we're going to be calling our factorial code. Notice I didn't have to do anything for the execution context. This context is part of the actor system. It's part of the actor. Every single actor gets one of these. So Akka provides you, inside of all of its actors, an execution context to use with futures. It's ready-made for doing things like this. It's a good fit, because a lot of times with computations, like I said, part of it you'll want to break up into actors, right? You want to do this part over in this machine, that part over in that machine, and then you want to bring them together into some central machine. So you want to do those individual computations like we're doing, like the factorial computations, in parallel on those individual machines, right? And this lets you do that very easily. You know, you don't need to build your own execution context. The actor system just provides it for you. All right? So we take our input, and then we have to switch on a few things, right? So this is the trivial case, and nothing to do is defined here, which is you just return 0 in the in n choose k. Return 0 for most cases. And then I break it up into a few things that we'll dive into, right? So the perform function is where this actor will do its work, and this context flat become says that I'm an actor, I'm going to do something else later, right? So this receive function says what to do with the actor, right? It says when I get 2 ints, I want to run my my n choose k computation. This context dot become says that I don't want to do this anymore. I want to do something else for the next message that comes in. And if we get a failure, we let it crash. This context dot stop self says I'm stopping myself. I'm not going to do any more. I'm just going to crash and end, right? Because we don't care about any other types of results, right? All right, and that's the way that Akka recommends you handle exceptional cases. Is you let the actor crash, and then the actor system can handle cleanup for you. All of the Akka documentation goes that way. Tells you to just let it crash.
Should it be context or should it be EC? You define the implicit value EC.
Mm-hmm. Yeah.
So when it says context becomes that.
Oh, okay. So this is a built-in function with the actor. Is context.become. It just says that I don't want to be this actor anymore. I want to be a different actor now. Yeah, that's all it does.
EC is context.dispatcher, but context.become is something different.
Oh,
Yeah.
they're just a coincidence.
Yep.
Well,
Yeah. Well, it's just inside the same. So the actor provides. So the context object provides a lot of helpers for the actor itself. So when you spawn this actor, this context object gets created. The context object comes with a dispatcher, which is an execution context. It also comes with a bunch of functions to help you deal with the actor. One of those functions is become, which says, I'm an actor, I want to change my behavior. Another one of those functions is stop, means I'm an actor, I just want to be done. And there's a whole bunch of other things that it comes with as well. Yeah. And Akka provides all of this for you. Yeah.
A pattern I've seen is a dead letter that is sent by an actor.
Yeah.
Is there one present here that I'm not aware of, or
No, so
would one use a?
Yeah, so this won't do dead letters because this case catches everything else. So this is else. So you can have multiple cases here, and this is a very specific thing. This wants 2 ints. That's all it wants. This underscore means I want anything, right? And these are just linear. This one happens first. This one happens second. So it just says if I have 2 ints, I want to do my computation. If I have anything else, I don't know what to do with this. I'm done. Yeah. Yep.
I have a question.
Yep.
What's the actual behavior defined by the Akka dispatcher, the execution context there?
The execution context, that's really complicated. Yeah, let's talk about that later. Yeah.
Okay.
Yeah, because the behavior is kind of complicated. That's why these things were built up, because like people got tired of writing these things and writing them wrong because it's really difficult to do right. So libraries happen. All right. Alrighty then. So moving on, we'll go on to define the perform and the compute, right? Which they actually do the work. So in perform, this is where we're going to do our dispatching, right? So we're going to take NK, and the actor that sent me the message that I'm working on right now, right? So actually, if we go back one slide, this first line here, this val sent by equals sender, you always want to do this. So Akka is message based. So you receive a message. In order to give the result back, you send a message back to the sender. So you can do sender.send the message. The problem with that is sender is a function. So it's the latest sender. Since we're doing asynchronous computations, another message from another sender could have come in by the time I'm done. So now the sender function is pointing to not the guy I want, but to some other person, right? So you always want to do this. You always want to take that sender, put it to a value, so you hold on to it forever. Yeah. All right. So that's what we take in here. We take in this reference to whatever sent us the initial message. All right, and then we get our n minus k. We do our trivial case. You know, if we have success, so we do the factorial, and this happens in the background. Remember, this is in a future. The do factorial function that we defined earlier, that's in a future, so that's asynchronous. So all of this happens asynchronously. If we're successful, we report a value of the numerator, because we're doing factorial then here. If we're not successful, then we just pass back a string and it'll fail in the sender. Yeah. And then we spawn. So this is context coming back, right? Another function it provides from Akka is creating child actors. So this computation has multiple levels. And how you define multiple levels in Akka is spawning new actors. So the top level actor gets spawned by the actor system itself. And then any actor that this top level actor spawns are actually under it in a hierarchy. So Akka actually literally has a hierarchy of actors. That's why it's really, really nice for hierarchical computations, because that's not just by coincidence or by or luck of the draw or anything like that. It's actually the way it's designed, down to its core, is hierarchical. Yep. So that's what we do. We create this actor for the denominator, and we pass it k and n minus k. All right. So there was another thing there, and so how do we compute the values, right? So we compute values by, yeah. So we wait for, so this is what we become, right? So we had an actor, and we did, right, context dot become compute. So we're no longer looking for 2 ints, right? 2 ints is what kicks off a computation for n choose k. Now we want to combine the values that we get. So we have a denominator and a numerator, right? At the top level, we have denominator and numerator, which we divide. All right. All right. All right. So this waits for a numerator and a denominator. So in an actor system, one way you can do this is you have vars here, and then when you get this numerator, you set it. You know, you decide what to do based on, is denominator already filled in? If denominator is not filled in, all right, I want to record that I have a numerator, and then just wait for the denominator. If the denominator is already there, then we want to send back the result of our computation, which is numerator divided by denominator, and we want to stop. We're done, right? Same with denominator, same thing happens, right? Bar is not my favorite way to do this. We'll see another way to do it later, but it's just one way to do it. I just wanted to show, you know, a couple ways where you could do this kind of computation. This is probably the simplest way. Well, I'm not sure. They're probably equally simple. It's just a different way of thinking, right? So we have our computations, which trade off on which one we know is happening. If we already have a numerator and we get a denominator, we're done. If we already have a denominator and we get a numerator, we're done. Otherwise, we need to keep on going, right? And again, let it crash. If we get anything else, something has gone horribly wrong, we're done, right? And again, just the let it crash mentality behind Akka's actors. All right. So this is the main actor, right? The top level, it spawns all the other actors, right? All it does is accept the input values for our choice operation. It dispatches events to other actors, to child actors, and then it combines the results and terminates. That's all. All right. All right. So now, so the numerator is done on the same machine as this is done, right? We saw that. We just put that in the future right away in the perform function, right? The denominator had 2 calculations, which we want to split up, right? So we put that into another actor, right? So this is the original thing for the denominator, the original functionality, right? It, again, takes 2 ints, and then it tries to do a computation based on them. And it lets it crash on a failure, just like always. And, well, it should. I did not put the context.stop in there, but we'll pretend it's there. And this just dispatches the left part and the right part to 2 smaller actors, right? And it becomes a has none. So it has no results yet, right? So this is, yep, again, changing state with that. So this is the other way that you can wait for multiple results to come back, keep them, and return the result at the end, is by using become, right? So has none waits for a left or a right, right? If it gets a left, I become I have a left. If it gets a right, I become I have a right. You know, has left waits for a right, has right waits for a left. And then each of them, once it gets what they're waiting for, it finishes, right? And here's the let it crash again on a fail. Always, always, always let it crash. Most of the time, I guess, yeah. So this is more like a state machine, you know. I'm in this state, so I'm waiting for these results. Once I get a result, I need to go to the next state, wait for another result, and then go to the next state and finish. So this acts as a state machine as opposed to the more imperative version of the last actor. All right. And that's it. I mean, that's the whole computation, right? It's pretty straightforward. To break that up into actors. You know, we started at the top. We knew we had to do a division and a multiplication. So we broke that up into 2 actors, a numerator and a denominator. And then we knew that the multiplication happened inside of the denominator, so we broke that up. And then the levels come up and combine to the top where we get our result. And that's it. So, yeah, futures are the standard for asynchronous computation, right? You go there first. It's in the standard library. Like, you install Scala, you have futures. It's really good for breaking up asynchronously linear computations. You know, you have something that used to be sequential, and you want to make it asynchronous. Go with futures first, normally, right? And you get a good bang for your buck here. You know, you invest some time, and it comes out. Actors are usually used for larger problems. They're way more heavyweight than futures are. You're usually going to get a drop in performance when you go to actors, but you get so much more power because staying inside of the actor context, it does so much for you. You know, it gives you an execution context to run your futures against. It gives you semantics for failure states that are way more powerful than futures give you. It gives you semantics for hierarchies that futures don't give you. Like to do a hierarchy in futures, when we did it, I wrote a recursive function that just made more futures inside of the recursive function, which is way more complicated than just saying, oh, just make another one of these things, right? So therefore more complicated problems where you can take that performance hit. And also they're for distributed problems. Futures don't work over the network. Actors do. Actors are ready-made for distributed programming. So if you have a distributed problem, go with actors. Yeah. And that's it. Yeah. It's that simple.
Our friends terms of the node world works
Mhm.
with callbacks.
Yeah.
Do you know what the difference is between callback and feature?
So, they're, it's pretty similar. So with a callback, it's a little bit less powerful, right? So when you do a callback, you say, okay, I have this computation, which is a click event. I don't know how long it's going to take, but I do know that when it's finished, I want to do this thing, right? So then you write a callback for the thing you want to do at the very end. It doesn't give you another thing, another asynchronous object back where you can then say, oh, at the end of that, let me do something else. Futures give you that. So that's one big difference is you can chain operations in futures, whereas callbacks are fire and forget. There's only one thing in there. That's probably
Callback hell.
yeah. That's why they call it callback hell, because now where am I in my application? You know, whereas futures kind of reel that in a little bit and say, you know exactly when, you know exactly what you can do at the end of your callback, right? And you can tell it what to do. So that's probably the biggest and most important difference there.
I wonder if they, the error state, like a future's like an option, right? Like it handles
Yeah.
if it didn't work.
Yeah, it's actually it's the asynchronous version of try.
I don't know very much about callbacks, but I don't know that they behave well in an error.
It depends on the framework. Yeah.
Usually you have to specify 2 callbacks,
Mhm.
which is actually exactly what
What you have to do in the
did.
future.
Yeah.
So JavaScript has something called promises, which are very similar to Scala Future.
Right.
Yeah. Yep. That's right. Yeah. Promises are like the other side of the future. Where like a future you say, I want to do this computation and I want the result back from it. A promise is, I am a promise. I'm going to eventually give you some result back. So they're like opposite sides of the same coin.
Are there only the two, you were talking about matching the problem to the solution, right? You know, like if it's a simple computation in the hierarchy. Are there only the 2 choices?
No.
Or just like hundreds of them and you just can get into it?
There are a lot. there are very, very many. So the next biggest one, I think, in Scala after futures and actors is probably Scala Z tasks. Would you say? They're used in a lot of places.
Probably.
So they're probably the next layer up there, and they're a little bit more powerful than futures. So there are a lot of things that you can play around with, and also futures are eager. So when you say future curly brace do this computation, it starts that computation in another thread immediately. Scala Z tasks are lazy, so it's only when you want to get that result where it starts to do this chain of operations.
If actors form a hierarchy, they're a tree of actors.
Yeah.
Does every actor on the tree have a name?
Yes. Actually, that's how they're addressed. They're addressed by a string, and that name has to be unique.
Okay.
Over the entire actor system.
Okay.
That specific name. So they get a full path, right?
So given that they have a name, and let's say that you're doing some sort of asynchronous computation. Let's say you have a forest of trees, like you're doing, actor computations on one machine and actor computations on another machine.
Yep.
How do you deal with combining, the trees in the forest, right? So like, let's say that you have one computation on a tree go through, and you want to connect it to another computation on another tree. How do you deal with? Is there like a easy way to deal with naming conventions from the different trees to form another tree, or
so this is yes and no. Akka does that for you.
Okay.
With its clustering. So you don't really have much control over that as the developer in Akka. You have some control where you can name actors, right, that you spawn yourself. But every actor has like a prefix to its name, which is basically which machine in the cluster it is part of. You don't have much control over that. And as far as combining the computations across nodes in the cluster, Akka handles that for you. Yeah.
Do you do pattern matching on the names of like the things on a tree?
Yeah, actually, so when I was talking about the sender, that actor ref, you can actually do that dot path, and that gets you the full actor name, the full path to the actor in your cluster. And then that's just that can be turned into a string. You just pattern match on that. Yeah.
You didn't want to use the word monad.
Yeah.
I don't know much about it, but I thought I recognized it. So it's when you
Yeah.
had the unit operator in the way of combining. Is that a monad?
The way of combining is, in this specific case, it's just a monoid. Right? It's not a group. It's just a monoid.
Just a monoid.
Yeah. So that's a that's a monoid. So a monoid is just basically it's just I have an identity, which is if I take that and combine it with any other value, I get the same second value out, right? And that works on both sides. And it has a way to combine things. That's all it has. Pretty much, yeah. So that's a monoid. When we were doing the for comprehensions with the flat map, so that's a monad, is where I'll have like a future, and then I want to take the value of that future, and from that value, I want to turn that into another future, right? So now I have a future of a future, but I don't want a future of a future. I just want a future. That's what monads do. Is it takes the future of a future and turns it into just a future. Yeah. Yep.
So I've never actually used it myself, but I assume there is also an applicative for futures that actually does run the calculations in parallel.
Yeah, Scholars that gives you that.
That's what I figured.
Yep. Yep. All right, awesome.
Akka HTTPS, where would names for actors be stored? Like, is there a particular...
Everything in Akka is inside of an actor system.
Yeah.
So you always have a reference. You can always get the reference to the actor system, and you can always get the reference to whatever you're running in through a context. Akka has myriad ways to get these things. So yeah, I mean, pretty much no matter what you're doing in Akka, you can get that context out.
So the initial thing that could spawn the first actor of the system would define the naming conventions for the...
Yeah, so the tree hierarchy in Akka is really complicated. It has all kinds of guardian actors, quote unquote, which are spawned immediately when you make the actor system, and they delegate things to the actors that you make. And you have no access to those actors, really. And they control, basically, the workflow over the entire actor system. And you can always get a reference to things in the actor system because of how strictly it's been written. You know, you can't do certain things for a reason, you know, and they provide them for you in the way that you should use them.
So you're putting your slides up someplace so we can see.
Yeah, I'll do that. Yep.
That's very helpful.
Definitely. Yeah.
Not just the slides, the source code itself would be great.
Yeah. I'll put that on GitHub. Yeah. Yep. And the slides probably too. But yeah, hopefully you have some kind of feeling about how to, you know, transform a synchronous computation into an asynchronous computation. and also some feeling about how to decide between actors and futures. You know, that was pretty much the goal. Just that, having that feeling of what to use when, and how to even get to a point where you're ready to do asynchronous programming. Because like in the very beginning of this, we did a lot of things to make it asynchronous and got no performance gain out of it, right? So just the way in which you have to think in order to lift something into the asynchronous context is challenging in and of itself. So hopefully I gave you some kind of feeling about that.
When you were doing we were going through this transformation,
Mm-hmm.
One way you could tell it wasn't working is because your runtime wasn't better.
Yeah.
Is there any other way that would have helped you if you're not an expert to figure that out?
Not really. Profiling is like, it has always been and still is like the end all be all in, am I doing better than I was yesterday with this code? You know, just profile. How much memory am I taking up? How long is this taking? The only way to do that is real world examples. You can figure this stuff out mathematically. Like I said, people used to prove their programs. I've done it before. You don't want to do that. you never want to do that. So you can go that route if you want, but I think it's more comfortable just to put a system.current time here and the system.current time there, and then subtract them.
You could do that through monadic logging.
yeah, monadic logging, and then you just put it right into the computation. It's a nice plug.
So do you have any good Scala blogs to recommend?
Yeah, I mean, there are a lot of, so the best thing to do is, are you on Twitter? There are certain people that you can start following on Twitter, and then that'll lead you to follow certain other people on Twitter, and then this just grows. And then all of those people's blogs you can look for. So I mean, when I was first starting out with Scala, some of the blogs, some of the Twitter contacts that I first got, and it worked out pretty well for me, were Michael Pilquist. He's really good to follow. He's just M. Pilquist. And who else starting out? Miles Sabin. Yeah.
He might be a
but he posts he posts a lot to Twitter of other people's posts, which are at like a low level. You know, so he's like, this was a great treatment of whatever, you know, and he doesn't post his own stuff ever, which is great. And then but he'll introduce you to a lot of people. So I'm just gonna list off some Twitter handles. D6, T Polecat, probably is really good. Adalbert, yeah. What's his Twitter? Is it just Adalbert Chang?
It's Adalbert
Yeah.
Chang.
Adalbert Chang, yeah. Yeah, he's really good too. Yeah.
One blog that I know a lot of people at Drenaya really like is the Neophyte's Guide to Scala.
Yes, I forgot about that. Yes, absolutely.
That one's a really good primer on a lot of concepts.
Mm-hmm. Yeah, the Neophyte's Guide to Scala is like is one of the best entry-level Scala documents I've like ever gone with. That's how I learned Scala initially. Is I Googled and Googled and Googled and found a whole bunch of stuff about words that I didn't understand, and then I found the Neophyte's Guide to Scala, and that was like the breaking point. That was like the one thing I could actually read at that point. You know.
You recommended me the Red Book, and I got it, started reading it.
Yeah. Oh, he knows math. Yeah.
Oh, okay.
Yeah.
So other than that, I do a lot of functional programming in R, so like I'm comfortable with the functional concepts.
Yeah.
Just is there like what would be a good like resource for someone who likes math to learn Scala?
So he likes math to learn Scala. So I mean, the Red Book is like really good, and then anything on on learning Scala Z.
Scala Z?
Yeah. That would be good.
Yeah.
Like if you just do that.
Or
I think
cats.
yeah, Scala Z or cats yeah, pretty much, yeah. Scala Z and cats.
Cats?
Yeah, cats. 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 So just
I'm
type
wearing my cat
Scala
shirt.
cats?
No,
type
cats.
level. Yeah, just type in type level cats into Google and you'll find the
Just
GitHub.
Google cats. You'll find it. It'll be the first
Nah,
one.
yeah, do not Google cats. No. But yeah, type level cats and that'll hook you up pretty good. Yeah. Yeah.
When you talk about actors, you say it's not typesafe. You mean the message or?
Yeah, so the message passing interface is any. You just get an any back from the actor. And then you have to pretty much pattern match on it or as instance of on it or something like that in order to get to the type that you want. So the compiler cannot help you in the actor-to-actor boundaries, But that's the price you pay.
You mentioned that some good listening can help with that. And what are they?
So Akka has a test framework for testing your actor systems, and it's really, really good. Like you can test most actors inside most operations that you're doing with your actors between message passing. You could probably test inside of 5 lines of code. So if you just it's called the Akka test kit, and if you just pull that into your SBT build, then you can just write those tests, and that uses Scala test. So it uses all the standard stuff and language that you're used to from that. Yep. So yeah, write your tests. Treat your actor system like JavaScript. It's because it pretty much is. It's dynamic. You're not going to know it's going to crash until runtime. You get the wrong input, and you really want to know that before runtime. Yep. Yep. All right. Yeah, I think we're good. Yeah, I'll post the slides and blah, blah, blah and everything to the meetup page as well. I'll post it there. And then I'll just post links to like GitHub or wherever everything is.
Thanks, Summer.
Yeah, all right. Awesome. All right. Holy shit.